Hey everybody, it's Ripley back again. We're going to talk about Green's theorem. Green's theorem is going to make your lives really, really simple. Trust me, and I'm going to show you how here in just a second. I'm not going to get bogged down in the formal proof. We'll go over that in class. We'll take a look at how it works. It's not a very difficult proof, but I'm trying to get these last few videos in under like 20 minutes, and I know how crazy it makes you guys with the super long videos. So we need one more piece of vocab and a little bit of notation, and then we'll get where we got to get. Okay. So sorry, I'm a little too much caffeine this morning. We need to talk about something called positive orientation. So if I have a curve, all right. So let's say we've got some D. Let's just call this. All right, and this is my D down here. All right, and I've got a curve that goes around D. Now, I can either go around clockwise, in which case I'd have these guys, right? I have these guys and these guys, or I can go around counterclockwise. Let's go orange. If I go around the curve in a counterclockwise direction, that's called a positive orientation. Positive. In other words, think of it as though you're walking around D and it's always on your left. Okay? That's a positive orientation. All right? Now, I'm going to write out Green's theorem, and it's kind of a long theorem, so bear with me. It's not going to take too long. You can put me on 2 times speed right now. And then we're going to see how it works, because it's pretty powerful good. All right? So this is Green's theorem. It says, let's see be a positively oriented. This is where it gets kind of goofy. It's going to be piecewise smooth. You remember what that means? It means it doesn't necessarily have to be completely smooth. It just has to be piecewise smooth. In other words, as you build the pieces, they all connect. There are no jumps. And then every little piece is differentiable. All right, piecewise, sorry. Where am I? Smooth. I have to look this up. I can't memorize these. Simple. Remember what simple means? Simple, closed curve. Means there's no little tangles or anything like that. Curve, and it's closed, so it's got to finish where it's got to finish where it started, basically, for any point on the curve. As I follow this thing around, keeping D on my left, I finish where I started. Excuse me. Curve. And let D be the region bounded by C. All right. So this guy right here is C. And this is D inside. Let B be bounded by C. Now this is going to get pretty interesting in a sec. If P and Q have continuous partials, what am I doing? Continuous partials on the open region. Now here we go. Remember this? The open, what's it mean to be an open region containing D? It means you can pick a point, draw a circle, and everything in that circle, everything within that circle is also within that region. Now, clearly D is not an open region, because if we're defining the endpoints, I guess the interior of D would be open, right? But what we're saying is open the partials on the open region containing D. Containing D. So we're saying, in this case, R2 contains D. R2 is clearly an open region. Pick any point, draw a circle, you're still in R2. You haven't left it somehow. All right, then, and here's where the rubber meets the road. And this is where it gets really cool. The integral, so I've got the line integral of P dx plus Q dy. Now, we've dealt with these a bunch in the past, don't panic, equals. Now you may say, wait a sec, why would we want to go from a single integral to a double? Well, we're going to talk about that here in just a sec. This is going to be the double integral over D of the partial of Q with respect to X minus the partial of P with respect to Y dA. Now we've seen this before. Remember, if these two things are equal, then we know that our vector field is conservative. So Green just sort of piggybacked on that. He was like, all right, well, I'm going to prove some stuff. And what I can prove is that rather than taking a simple line integral like we know how to do, we can actually do a double integral over a region. And again, I know you might be saying, why are we taking a double when we can take a single? Well, I'll show you why here in just a sec. But before we get there, we need a little bit of notation. Sometimes this line integral, if it satisfies all of this right here, in other words, if it's positively oriented and closed, all right, if C is a positively oriented closed curve, we'll write this, and you'll see this in physics a lot, excuse me, because we have these force fields, all right, that are typically closed. And we can at least write them, depending on perspective, as positively oriented, right? If we don't like the orientation of the curve in physics, we just look at it from the other side of the field. You know what I mean? It's kind of like looking at an electromagnetic field, and if I don't like the way it's oriented, I can just go to the other side of the electromagnetic field so that it rotates the way that I want it to. Think of it as looking at a fan, right? If I don't like the way a fan is rotating, if I want it to rotate the other way, I just go to the back side of it, okay? All right, so this is P dx, P dx plus Q dy. All right, sometimes you will also see this. This seems a little overly notational to me, but you'll see this written with a circle, and then this guy will have a little arrow right there, and this is P dx plus Q dy. Okay, now I have to answer the question, why? Why do we use this? And I'm going to answer that question with a problem. I'm actually going to do an example straight out of the text, all right? And that example is, we're going to take the line integral, right, over a closed, positively oriented region, positively oriented curve of xy dx plus y squared, plus x squared y cubed dy. And we're going to define, let's say, where C is the triangle with vertices, with verts 0, 0, 1, 0, and 1, 2. Okay? All right, now we're going to do this example, but we're going to do it both ways. We're going to do it this way with a single integral, and then we're going to do it with Green's, and you're going to see why Green's is such a powerful theorem. It's really, really useful, and it can help us expedite a lot of these line integrals when we're getting them done, okay? Okay, so let's make this thing happen. All right, so here's our crazy vector field, right? But we're not going to worry about that. What we're going to worry about is, what does this thing look like? What does this path look like? So here's 0, 0, here's 0, 0, here's, well, we better not get too crazy, right? Here's 1, 0, so I got to go up 6, 1, 2, 3, 4, 5, 6. Here's 1, 2, and then this is our guy. Now, what we have is we have a path that's, well, we can start the path anywhere, but I mean, let's keep it simple. We have a path that starts here. It's got to be positively oriented, so we got to go around this thing, around this curve counterclockwise. So it's going to go this way, right? You agree with that? Our D is inside. This is the C that we're calling the path. All right. Now, if I want to do this in the conventional manner without Green's theorem, what do you notice that I have to do? Well, I need to write C, this curve, this path, as C1, C2, C3, as this piecewise smooth curve. Well, that's not too hard, because if you look close, what's C1 going to be? Well, C1 is going to be, I'm going to need a little bit more room. C1 is going to be, well, it's got to be parameterized, right? So I'm going to let x equal, let's see, I'm going to let x equal t. I'm going to let y equal 0, right, because it stays 0 the whole time. Dx is equal to 1 dt. Dy is equal to 0 dt. And I know this is going to be for t between 0 and 1, right? That's easy enough. What's C2? Well, in this case, all right, so C1, then I go up here, right? Now x is going to be 1, so x is 1. And I'm going to let y equal, what would I let it be? Just how about 2t? That works, doesn't it? Because then when t is 0, y is 0, which is what I want. When t is 1, yeah, y is 2. I'm all good, right? Let's see, dx is equal to 0 dt. dy is equal to 2 dt. And then this again is for t between 0 and 1. Now you may say, Rivley, whoa, 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 whoa. We're supposed to be traversing this thing. So it's supposed to be a walk. Why am I allowed to parameterize on the same parameter from 0 to 1? Well, it doesn't matter. As long as we're moving from left to right around this thing, for whatever t we create, we're good. Now, left to right doesn't make a whole lot of sense when I'm going vertically. But in the context of this, I need to be moving up these vertical parts of the piecewise smooth curve, don't I? Otherwise, it doesn't make any sense. If I wanted to, I could parameterize 0 to 1, 1 to 2, 2 to 3. But at the end of the day, the mathematics, and you can check this for yourself, it doesn't matter. I can put them all in the same parameter. I can put them on different parameters. As long as I'm accounting for this positively oriented path, i.e. D, remember D is this guy in here, D is always on the left-hand side as I walk around. Okay, so C3, I don't want to get bogged down too much in that. Hopefully that's not too confusing. All right, now I start at 1 comma 2 lives up here, and I got to finish at 0, 0, and this is 1 comma 0, right? So, I mean, with a little bit of thought, I always kind of just tinker with these. I don't use that. Remember, we have the R naught times 1 minus t plus R1. That's a way to build a line segment in space using vectors, right? Times t. Remember this guy? You can write it like that. This is for t between 0 and 1. And if you can't remember how to build these, use that. But for me, it's more fun to sort of build a puzzle. So this guy's going to be what? I got to start at 1, I got to finish at 0. Oh, okay. So what? That's 1 minus t, right? Because if I start at 1, remember, I'm going with the parameter between 0 and 1. So when t is 0, I'm at 1. When t is 1, I'm at 0. And this, remember, this only works for lines. If this was anything other than a line, I'd be in trouble. This is going to be y is equal to, okay, this is a little trickier. Now I got to start at 2 and finish at 0. Well, that's not bad, right? It's just going to be the same thing, only it's going to be 2 minus 2t. Start at 2, if I put t in for, yeah, that works, doesn't it? So dx is equal to, what is it, negative dt. dy is equal to negative 2 dt. And t is between 0 and 1. Okay? Now, deep breath. We're going to write this line integral, and you're going to see what happens. So the integral, a line integral over c of x, y, I'm going to need the next page, but that's going to bum me out. All right, that's all right. I think I can memorize this thing. Dx plus x squared y cubed dy is going to equal the positively oriented closed line integral over c. But instead of c, because it's piecewise smooth, we got to go c1 plus c2 plus c3, right? Because that's how many chunks in the piecewise smooth curve we have. Excuse me, of x, y, dy plus x squared y cubed. Whoops, I said x, y, dx. Don't listen to me. Boy, I got crazy. You guys know me. I make errors, but I try to catch them as I move past. All right, so on the next page, we're going to start writing this thing out. And once we write it, you're going to be like, oh, dear goodness, what's happening here? All right, so this becomes the integral. And I'm just using the information. Luckily, I wrote this down on the side. I'm using this information right here. I would really like you guys to see where this comes from. But hopefully you wrote it down as well. Well, if you didn't, you get what you deserve. So that integral becomes, I'm going to write a big old equal sign here. It's going to be the integral from 0 to 1 of 0 times 1 dt plus t squared times 0, I could say 0 cubed, times 0 dt. Now this accounts for c1. This is going to be plus the integral from 0 to 1 of 1 times 2t times 0 dt plus 1 squared times 2t cubed times 2 dt. Now, over here, as you can probably tell, this is just going to give me a big fat 0. This chunk's going to give me a big fat 0, but this is going to give me some interesting stuff here. This is c2. And then we have to add in C3, right? So that becomes plus the integral from 0 to 1 of 1 minus t. Now here's where the rubber sort of meets the road. Times 2 minus 2t. This is that xy. And then this is times negative 1 dt. And then plus 1 minus t squared times 2 minus 2t cubed times negative 2 dt. Now you can already probably tell that this is going to be really ugly. All right? Now I do want to sort of walk you a little bit through how to do this thing, but if you'll see what happens. It's going to be sort of a cooking show at the end where I'm all poof and your answer is, but don't panic. So this top C2 portion of the integral becomes the integral from 0 to 1 of, let's see, what's that? That's going to be 16t cubed dt. That's that part. This chunk right here is going to be plus the integral from 0 to 1 of, now I'm going to factor this 2 out. So I'm going to get a negative 2 out in front. Let's put that, well, we'll just stuff that negative 2 right there. You see where that negative 2 is coming from? I'm factoring a 2 out, and I'm getting 1 minus t squared dt. So that's what this guy turns into. Plus, now this one's a little trickier. I'm going to pull the 2 out, but it's got to be cubed to give me an 8. So I get plus negative 16, because that 8 times that negative 2 gives me that, times the integral from 0 to 1 of 1 minus t to the 5th dt. Now, you're already, I'm sure your eyes are rolling back in your head like, oh, Ripley, what's going on? I don't want to have to do these. It's actually pretty easy. This becomes 4, and then these guys each become, this is negative 10 thirds, this is, I'm sorry, negative 12. Wait a sec, I'm sorry, this is negative 2 thirds, this is negative 8 thirds, so the answer becomes 2 thirds. And you may say, well, how did you do that? Well, you just do a quick u substitution with this. I'd let u equal 1 minus t, du equals negative dt. You putz around with these limits and you be really careful, and you end up with 2 thirds. All right, I'm exhausted. Or using Green's theorem, if I use a little gt, and what's Green's theorem say? Well, Green's theorem says the line integral over c of p dx plus q dy is equal to the double integral over d of the partial of q, q with respect to x, minus the partial of p with respect to y, right? So remember, this is our positively oriented connected curve over C, right, or around C, however you want to call it, of, and what was this? This was x, y, dx plus x squared y cubed dy. Now, I'm just going to use this fact. I'm going to use Green's theorem because all this madness that was going on, like this took a really long time. It was really hard. Well, let's look at our region first because I forgot my dA over here, didn't I? I need to figure out what my region is defined by. Well, if this is the point 1, 2, then can't I rewrite this integral? This is simply, it looks as though x goes from 0 to 1, so we'll put him on the outside, and y goes from 0 to 2x, right, from down here to up here as I move my way. Remember, sorry, I'm getting all crazy. The bell's going to ring in like 2 minutes. Sorry, guys. And then I take the partials, right? Partial, this is p, and this is q, and I take this partial with respect to x, so I get 2x y cubed. And from that, I subtract the partial of p with respect to y. That just gives me x. And then apparently I'm going dy dx, right? I work inside out. And watch how nice this is. Well, this becomes the integral from 0 to 1 of what? Well, this is going to be what? Y to the 4th, so it's going to be x y to the 4th over 2, right? Minus xy from 0 to 2x dx. This is equal to the integral from 0 to 1 of, let's see, I got to stuff some stuff in here, don't I? 16x to the 5th. 16x to the 5th over 2 minus, what do I get? 2x squared? You guys buy what I'm selling? 2x squared dx. And this becomes, what's this become? I hope this all becomes 2 thirds. I'm going to have to redo this damn video, and I don't want to do that. Let's see, 16 twelfths, that sounds like 4 thirds. 4 thirds, whoops, don't get your 0 to 1 there, you dingbat. Sorry, guys, I'm a little rushed here. I apologize. 16 twelfths is 4 thirds. So this is 4/3 x to the 6th minus 2/3 x cubed from 0 to 1. Well, hush my mouth. That's 2/3. Oh, Ripley, I think I like Green's theorem a little bit better. You see how much faster that was. All right, cool. Well, there's one more ramification of Green's theorem, which we'll go ahead and discuss it in class because I'm going to run out of time on this video. It doesn't take very long, and it's relatively straightforward. It's pretty intuitive. Thanks for your time and attention. Green's theorem rules, for those of you who haven't figured that out yet. I'll see you in class. Have a great day. Bye.